Hello, my name is Ramin Hojjati, and today I will be giving a short demonstration of the sequential equivalency checking features of Solidify. I will give this introduction using an example. This example is called CPU-IF and is a controller containing a register file, state machine, weight counters, and various other glue logic. We have implemented this design in both Verilog and VHDL, and these implementations are different and have different number of registers. But our goal is to prove that the two designs are input-output equivalent. That means that if the two state machines are properly reset, then for all input sequences, the output sequences are also the same. As you could see, this machine has 49 outputs and I believe about 26 inputs. So I will use the shell capabilities of Solidify to demonstrate this. Let me bring up Solidify shell. And actually before that, I'm going to remove my work directory. And the first command that we have to run is this command called make EC project, and EC stands for equivalency checking. And what that does pictorially is as follows. So it takes the original RTL, which we call a specification or spec, and puts that in the same top level as the implementation or the modified RTL. It ties the two inputs together because the inputs have to be the same. And then it leaves the two outputs sets, and then it writes a property file that specifies that each sets of corresponding outputs have to be the same. So looking at this command again, this is the name of the design. It could be anything. Then the two designs are specified using these files, and if we look at them, we'll see these are just listing files, and the first design is a Verilog design containing one Verilog file, and the second design is a VHDL design, and it also has only one file. We have to specify what the top modules are. When you specify a design, there could be multiple top-level modules, especially if you have library files. So the top level has to be specified. In this case, is CPU-IF, and the work directory has to be given. So we do that. And here the design is built, the combined design is built. And really there are two main artifacts coming out of this process. One is a Verilog file, in this case, specifying the combined design. And you can see we have one set of inputs, we have one set of outputs for the specification, and then we have another set of outputs for the implementation. We have an instantiation of the spec, and then we have an instantiation of the implementation. The other major artifact is the property file, and then we have 49 of these. For each output, we specify that that output in the spec is the same as the output in the implementation. So you could see here for the acknowledge signal, we're specifying that specification and implementation correspond to one another. So normally what would happen at this point is you would go to final verification and you would tell a tool like Solidify to verify that all those properties are the same. But we can do much better in the case of sequential equivalency checking and make the process much faster. And we do that by a process that we call finding matches, and that goes through the two designs and identifies all the flip-flops and signals which may be identical. So if you apply reset and you let the design run, those two signals of flip-flops always have the same values. These are just candidates. These are not proven to be the same. There are various techniques that find those candidates, and this is fairly sophisticated technology. So we run this command, and I'm sending the output to a temporary file, and we could look at the end of that file, and that has run. Now the next step is a process we call simplification, and what it does is that it uses formal verification technology and additional algorithms, and it takes those matching files and tries to verify the ones that are the same and also disprove the ones that it can find counterexamples. And at that point, you could say these are not matching. So let's go back and run this command. And here it goes. And the major artifact of that one is a matching file. And I didn't show you the matching file in the previous version. Let me see if I have it here. So this is the original matching file that had been produced. And you can see it says that, for example, this data out 0 signal in implementation is potentially the same as the corresponding signal in the specification. Now the new matching file, let's use here, and you can see it contains nothing because all those pairs have either been proven to be the same or there have been counterexamples that have been found that shows that they do not hold. All right, so the final step is doing a final verification now that we've gone through those steps, and the final verification in Solidify is called auto verify. So we run auto verify, and we will go and look at the tail of that. And you could see there were 49 properties and they all passed. So I would like to say a few words about the timeline of the development of this feature. We started working on this feature in 2003. To some degree, it was driven by a major semiconductor company that was collaborating with us. And we spent about a few years focused on improving the property verification engines with respect to the problems that were coming from sequential equivalency checking. Eventually, we had a dedicated team that looked at specialized algorithms for SEC, and they worked for about 3 years. And then had some beta release, and it went through testing. And in 2010, we had the first commercial release of sequential equivalency checking. And we'll continue to have collaborations with major customers and partners. And part of that was identifying that combinational equivalency checking can help in speeding things up. And so we developed one and included that. The point of this is that there's a lot of technology in Solidify's SEC, and we have just scratched the surface of it. But this concludes this video.